Hi everyone, we're going to talk about factoring basics today. So I'm making this video under the assumption that at least some point in your life you've already have seen factoring, maybe in Algebra 1, maybe you had a crash course through it when you were going through geometry, but either way, this is not for anyone who has never seen factoring before. If that's you, then maybe I need to make a longer video. But for my Algebra 2 kids, this should be enough. So factoring basics, the things that we need to review and remember is GCF. Greatest common factor is the name of the game whenever we're doing factoring. So the very basics of it is, let's say I have two numbers, and that's usually the idea. If I'm looking at multiple terms, multiple numbers, what do they have in common? That's where the greatest common factor comes in. So let's say I have 8 and 64. Two different numbers, two separate numbers. Well, what do they have in common? What are some factors they have in common? Well, they can definitely be, they're both divisible by 2, they're divisible by 4, but I think the greatest common factor is that they're both divisible by 8. So if I factored, let's say this is 8 plus 64, if I factored out an 8 from both of these numbers, then what would I be left with on the inside? Think of this as reverse distribution. So 8 times what would give us 8? Well, 8 times 1 gives us 8. And 8 times 8 gives us 64. So by factoring out 8, we're left with 8 times the quantity of 1 plus 8. Now, this doesn't mean much when we're only working with numbers, because clearly, if we wanted to, we could just add 1 plus 8. It's much more interesting when we're working with variables and terms that are not like, things that we can't add together. So let's say we have, maybe 4x squared plus 8x. So we have 4x squared. X squared cannot be added to x. They don't have the same exponent, and 4 and 8, we can't put those together because they're attached to the x squared and the x. So we need to factor to at least get it into its most simplest form. So we know that 4 and 8 have 4 in common, so I could definitely factor out a 4. But if I look at x squared and I look at x, well, x squared, that's just x times x. So both of these, x squared and x by itself, have x in common. So if I factor out x, I'm left with 4x times what would give us 4x squared? Well, 4x times x would give us 4x squared. Remember our exponent rules that if I have, let's say, x just by itself, that's really x raised to the power of 1. And if I multiply it by another x raised to the power of 1, then our exponent rules say that we should add these exponent values to give us x squared. So we're left with x times 4x gives us our original 4x squared back. And 4x times what gives us 8x? Well, if we just multiply it by 2, 4x times 2 would give us 8x. And this is our most factored form. There is nothing left from x and 2 that I could factor out, nothing that's common. So it gets more interesting when we talk about probably what you've seen so many times, and that's quadratics from Algebra 1. And in quadratics, we usually had trinomials. So nomial just meaning terms, and tri meaning we have 3 terms. So let's say we had, let me think of a good one, maybe x squared plus 14x plus 48. We have a trinomial here, 3 terms, and we want to try to turn this into the multiplication of 2 binomials. So I know each of these are going to have 2 terms each. 2 binomials multiplied together. So the process of getting from here to here, I'm sure you've done the other way around using the FOIL method, since that is so popular and common. But the proper mathematical term for this is binomial distribution. Because we know anytime we see parentheses and we're multiplying anything by that parentheses, we're really just distributing. And since they're binomials, we call it binomial distribution. It just happens to be that FOIL is a really neat and a clean way of doing that in a proper order that'll always work. But that's, you probably remember how to do FOIL. First, outer, inner, last, that one's not too difficult. The trick is remembering how do I go from the trinomial down to the two binomials. Well, I've seen my students say they've used the cross method where they have two numbers multiply to a times c, and those same two numbers have to add up to b. And where these letters are coming from is that, let's say I look at this x squared plus 14x plus 48, then the standard form of any trinomial, or especially quadratics, is ax squared plus bx plus 48. Oh, sorry, not 48, plus my last term, c. So in this case, if I was going to use this pattern, then my cross method would tell us I need two numbers that multiply to what's my a. My a happens to be 1 in this case because there is no coefficient in front of that x. So 1 times my c value, 1 times 48 is just 48. And I need them to add up to my b value. My b happens to be 14 in this case. So I need two numbers that add up to 14 but multiply to 48. And I've seen many students use this cross method to organize that information. But let's talk about why we really need 48 and 14. Well, first off, we know that, let's see, the factors of 48, that'll probably work. 6 times 8 is 48, and 6 plus 8 is also 14. So those two numbers would be 6 and 8. And if you remember, all we have to do now is fit these into our binomial and say, well, my answer in factored form is x plus 6, because this is positive 6, and x plus 8, positive 8. And if you checked your work by foiling, so first, outer, inner, lasting, this binomial distribution, you should most definitely get back x squared plus 14x plus 48. But I want to talk about why on earth does this make sense? Why do I want two numbers that multiply to 48 and they also add up to 14? Well, it's still just factoring. It's still factoring by grouping. And the idea is this number, 14, I could write that in any number of ways. I know 14 is, what's another way I could write 14? I could say, well, that's just 12 plus 2. I could say it's 10 plus 4. There's so many different ways I could write 14, and that goes the same for 14x. So what if I rewrote this 14 as these two numbers that supposedly will give me my answers? Well, 14x is the same as 6x plus 8x. So that's all I did. I changed nothing about this equation other than rewriting this number 14. So what's really cool about this is now I can do something called factor by grouping. So let's say I have x squared plus 6x plus 8x plus 48. Well, mathematics rules tells me if I want to, since these are just addition symbols, I could put parentheses around anything I feel like and say, well, I'm just grouping them. I'm focusing on these two things as separate entities first, and I'm allowed to do that. And now I look at x squared plus 6x. Well, now I go back to GCF, my greatest common factor between x squared and 6x. I can factor out an x. And what am I left with? X times x would give me x squared, and x times 6 would give me 6x. And I can do the same with this other grouping. 8x plus 48, well, the only thing they have in common, my greatest common factor, if I factor out an 8, I'm left with x plus, well, 8 times 6 gives me 48. So now I have x times the quantity of x plus 6 plus 8 times the quantity of x plus 6. But distribution rules and my multiplication rules tell me that this x plus 6, well, that's something in common. That's the greatest common factor of this entire expression now. Well, I can factor that out. So I factor out x plus 6 from both of these, and I'm left with x plus 8. And that is the mathematical reason why I can go from this step all the way down to this step, and why this cross method makes sense. And I think, personally, rather than viewing it as, well, I just need these numbers to multiply up to this and add up to this, it's nice seeing mathematically why all of this logically makes sense and works. And it'll help much more when our a value is no longer 1, because this was just 1 times x squared. When that a value is a number, this grouping will make our lives much easier. So let's look at another example, one that has a little bit of a curveball. X squared plus 20xy plus 100y squared. I'll give you a second to think about how this is going to turn out. It's very, very similar to what we did up here, in that at the end of the day, the only math that we really need to think about is, well, we still need two numbers that multiply up to 100 and two numbers that add up to 20. And that's especially because my a value, once again, is just 1. That makes our lives much easier. But the curveball is this y squared. Well, what do we do with that? I think the factor by grouping will make it make more sense than saying, well, at the end, I know the first terms, because remember, FOIL is how we go back from my binomials up to here. So I know my first terms are going to be x. That's always a given. But since I have a y squared here, my last terms will also need a y, because y times y is what's going to give me that y squared at the end. But rather than just saying that and saying that, well, it makes sense that they should fit there, factoring by grouping makes all the more sense. So I need to turn this middle term here, 20xy, into something that makes sense. What should I split 20xy into? Well, I needed to multiply to 100, and if I make it 20 is the same as 10 plus 10, and 10 times 10 is definitely 100. So let's rewrite this as 10xy plus 10xy, because 10xy plus 10xy definitely gives us 20xy, the same exact thing. So this and these two terms represent the same number, plus 100y squared. And now when we do our factor by grouping, this makes much more sense. So let's group the first two terms. Let's group the last two terms and see what we can find as a greatest common factor in each. So for the first, x squared plus 10xy, well, clearly I can pull out an x. I think that's all I can pull out. So x times x gives me x squared, and x times 10y gives me 10xy. And for the second grouping, I have 10xy plus 100y squared. I think I can pull out 10, because 10 is common to both 10 and 100. And there's a y here and a y squared. So I think I can also pull out a y. Can't pull out x, though, because this second term doesn't even have an x. So 10y times x would give me 10xy. And 10y times 10y would give me 100y squared. And fantastic, I have now two common factors, my greatest common factors between this addition, x times the quantity of x plus 10y, plus this whole separate entity. The greatest common factor is x plus 10y. The whole parentheses there is the greatest common factor, and I'm left with x plus 10y. And great. Now it makes total sense why I should have x plus 10y and x plus 10y. If I FOIL these out, I will definitely, most definitely, get back my original equation. The last thing I want to talk about is a very special case of factoring that takes place, especially around Algebra 1. And it's so special, in fact, that it has its own name. The difference of two squares. So it's so special because, one, we can generalize it and turn it into sort of a formula or basic algorithm that will always happen the same way over and over. But rather than show you guys that, let's go into, well, why it makes sense. So let's say I was given two binomials, x plus 4 and x minus 4. Now, I won't spoil the surprise, but there's a very important reason why I've picked x, and why I picked 4 and 4, and why there's an addition, and why there's a subtraction. Think about that for a moment. See if you remember from Algebra 1 why this is so fantastic. But if you don't, all you have to do is FOIL it, and it should become very clear. So, first, outer, inner, last, let's do a different color. First is x times x. Outer, my FOIL, outer is x times negative 4. My inner is 4 times x. And my last is positive 4 times negative 4. If I put all those together, first, x squared, plus outer first is negative 4 times x is minus 4x. Inner is positive 4x time, and then last is positive 4 times negative 4 will give me negative 16. Now, the reason why this is so special is because my minus 4x and my positive 4x, well, obviously, that'll reduce down to 0. And I'm left with x squared minus 16. And this is where the name difference of two squares comes in, because actually, it's missing a word that, honestly, I think we should keep in. Difference of two squares, it rolls off the tongue nicely, but it should really be difference of two perfect squares. Because if I take a look at x squared and negative 16, these are, in fact, perfect squares. And if you don't remember what a perfect square is, all that means is, if I square rooted a perfect square, it will give me a clean whole number. And it divides evenly. So let's say I have 16, that's also a perfect square. Well, the square root of 16 is 4. 4 squared is 16, the square root of 16 is 4. This makes 4 this nice, clean, even, perfect square. So if I have a difference, and that's the very important part, is it has to be a subtraction at the end. The difference of two perfect squares, then this binomial distribution will always come about, where I have x. Well, x is the square. And 4, well, when I square root 16, I get 4. And I always end up with two binomials, one having an addition and one having a subtraction. So let's say I put this formula to the test. Maybe I have, would be a good one. Oh, here. X cubed minus 25x. Well, this doesn't necessarily look like a difference of two squares yet, because x cubed, well, that's not a perfect square. But remember, whenever we factor GCF first, always, is there a greatest common factor I can mess with first? So, if I factor out an x, I'm left with x squared minus 25. Now, I have a difference of two squares. X squared is a perfect square. 25 is a perfect square, and they are indeed being subtracted. So forget about this x for a while. We'll leave that outside. That stays with us the whole time. But for now, if I follow the pattern, this difference of two perfect squares will become the binomial multiplication of the square root of whatever those perfect squares were, and having an addition and a subtraction. So the square root of x, that's x. The square root of 25, that's just 5. And then I'll have an addition on one and a subtraction on the other. And lastly, one final misconception I want to get out of the way. Speaking of difference of two perfect squares, let's talk about the importance of these actually being the difference. So let's say I have c squared plus 81. And immediately your eyes and your mind might think, well, that's a perfect square. That's a perfect square. 81 is just 9 times 9. I should make this c plus 9 and c minus 9. Well, that won't actually give us the answer we want, because I need to have it be a difference of two squares, and this is clearly the sum of two squares. Won't work, because without that difference, I'm not going to get a positive and a negative number that cancels out like it does here. So you might think, well, maybe this is just c plus 9 and c plus 9. Well, no go, because if I FOIL these two numbers, I get c squared plus 9c plus 9c, and then finally 9 times 9 is 81. And we know that c squared plus 18c plus 81, this is most definitely not the same as c squared plus 8. These are not the same. And in fact, c squared plus 8, I can't factor it at all. There's nothing I can do to it. There's nothing I can pull out. It's unfactorable. And a mathematical way of saying that something is unfactorable, or that I cannot find a GCF, or I can't divide it evenly by anything, I call it prime. So c squared plus 81 is actually a prime number. It's unfactorable the same way that 7 is unfactorable, or the number 3. They are only divisible by themselves in 1, or all the other numerous prime numbers that there are. But c squared plus 81, definitely not factorable.